Cool. Ready to start? I'm calling it day one, but really, you had a full day of classes yesterday. Or not. Maybe you're like Monday, Wednesday, Friday. Done. Do you know why we're here? What class this is? Applied Mechanics 2. Nice. All right. Give a second for people to be like, slowly backing out of the class. Applied Mechanics 2. What is that? What is Applied Mechanics 2?
Engineering dynamics.
Engineering dynamics. Yep. Yeah. So we had statics. Now we're going to be like, all right, get ready for your mind to be blown. Sum of the forces, MA, not 0. So far, Husky CT just has one link. Over the next 2 days, I'll fill out the rest of our schedule for the semester, but I didn't want to dump a whole bunch of due dates all at once before we even met. Plus, we just got back from holidays. It's so cold. We need a break. But we got syllabus up and running. Spring 25. We have a discussion board at GitHub discussions. So this whole website is like an open educational resource that I kind of keep up to date all through GitHub. So there's a discussion board there. It has previous discussions on there, so you can do a search to see hey, was anyone working on homework 5, homework 3, and ran into a problem. So we'll at least introduce, figure out how to use it. This is great for if the class time doesn't work for some reason, then it helps to have a group of people using GitHub discussions for the board. We'll do a lot of in-class discussion of homeworks and quizzes and projects anyway. Or you can use GitHub discussions for discussing the readings of how does this connect to something. But anyway, that's our first kind of resource. Well, the website and our syllabus is all one resource. Everything on Husky CT is our main back and forth. Submit assignments, get feedback, resubmit if you want to change the grade, and then we'll do some Jupyter and Python work. Have you used Jupyter at all? Anyone? Some no's. Bunch of no's. No yeses. No little awesome. This will be great then. A whole new thing. You can add it. One extra little bullet list item on your resume or your CV. I am proficient in Python and Jupyter for engineering analysis. Boom. Look at that. Now you have a whole new realm of job opportunities that you can run into. I'm not expecting anyone to be proficient Python programmers, but you should be able to recognize, all right, this is what I'm trying to do, and when I read this code, it looks like whatever, it's creating an equation of motion, or these must be the forces because it's mass times that acceleration term. But if you're trying to do something, you're looking at the project and you want to do something different, if you're thinking man, I wish I could see what the kinetic energy is in this system, then I'm happy to you show me what kind of equation you want, and I'll send you the line of code that actually gets that done. And believe it or not, you'll actually learn to use Python pretty quickly that way anyway. But it'll be fun. We'll build stuff together, and we'll work on it in class anyway. So this is flipped classroom. So we'll do some work when the projects come up. We'll do Python stuff together. So hopefully we'll debug our way through any the main issues. And excited. I'm excited. I do everything Jupyter and Python. This whole website is all Jupyter notebooks packaged up into a GitHub webpage. So flipped lectures, have you done those before? Yeah. Yeah. Yes. Okay. Last semester I explained what a flipped lecture was, and then at the end they're like, "Yeah, we've done that before." Then why didn't anyone stop me? Like 2 or 3 minutes into that whole like monologue about the benefits of active learning and student-centered approaches. It's like, yeah, we know that already. We're good. But main thing is like there's a bunch of material that I suggest you kind of read and stay on top of, and then in class we'll work on like homeworks, projects. So let's run through like a quick example of when we get into module 1. There's kind of like what we want to do, big picture. What is module 1? These are materials, videos, and notes. Chapter 1 is kind of short, so I'd say you could probably read that just, yeah, 20 minutes or something. It's just a couple of pages. And then I give you like a few like focused areas for most of the readings. Like don't go and read all of chapter 9 in one sitting. You can if you want. You can read as much or as much as you want, but for the most part, just like this first 9.3 example is helpful for that one. And then there's like some stuff that I've written where it mixes a little bit. Again, you get like a little bit more of that like mix of here's some engineering thoughts and analysis, but also some Python analysis, so you can kind of see the connection of what we're working towards and some of the bridges. So there's those couple of readings and examples. And you can do that like as we're doing this homework, but in class when we start module 1, we'll open up problem 1.1 and say, all right, how do we start? And then we'll start that. When we finish homework 1, and hopefully by then you're kind of roughly done with reading, like when you turn in homework 1, reading is mostly done, and whatever review or background. Then we'll spend one class building quiz 1, where the question is like, how do you demonstrate these learning objectives? So like, what's an example or another thing that you could show? Like, I learned to do this one thing, but I can change it a little bit. Now I can do something else. So we can apply, and we'll build that, make an example. This semester we have I have 2 sections of dynamics. So on Husky CT, there's going to be 2 quizzes, a section 2 and a section 3. I don't care which one you do. Like if we build as section 3 an example where at the end you're like, no, I don't want to do that. Then you look at section 2 and you're like, but that looks better. Like it's totally fine to mix and match. You just have to do 1 quiz. I guess just do 1. It's not meant to be like a huge. The goal is like 20 minutes. Spend 20 minutes just a focused. This is how I can demonstrate that I understand this material. That's what the quizzes are meant to do. So we'll do that. Then the last step will be, for module 1, it's a little different. We're going to do like a project proposal, but like module 2 project, we'll open this up and in class look at a 4-bar linkage and show like what are the steps of the analysis and how can we change the design and actually do like some engineering work. It's kind of main goal. It's like we have equations, we have models, we have ideas. How do I use those to my advantage? Like build something new or reverse engineer something, or get better understand, like be able to use a model to understand something else that I can't measure or I can't quite get to. How's that sound for a goal? Some goals. Questions yet? Or questions piling up yet. Nothing burning. I know there are questions, but it's like, how are they just, are they, there's always questions, but is it, all the chapters that we're using, they're all hosted on Yukon Library, so you don't have to like buy a textbook. You can use the PDFs from Yukon Library. Right now we're watching in class a YouTube stream. One, so that I know the stream is actually happening, and two, so that it gets recorded. So there's always, you can always go back and look at lectures that we've done already. And again, that's, so some people like to watch the streams remotely. It's a very different experience because we're doing like work together in class. So if you're working from home on these assignments, it's harder to kind of interact and ask questions and work with other people. It's not impossible, but just know that it's a very different experience that if you're like jumping in remotely. And it's the only, when I started streaming, it's the only time that I've gotten a comment that said like, man, I wish I was in class. I'm like, wow, I've never heard that from anybody, but they've like, after watching videos for a semester, in retrospect, they're like, man, maybe I should have gone to a few of those. It seemed like it might have been helpful. Like that, all right, yeah, lesson learned. Next time you're in a Professor Cooper course. All right, so let's jump down into our course for all the fun logistics, or the stress inducing, I don't know, the big ticket items of like, how do I get an A in the course? So, and the reason I'm jumping here is I was just talking about like, it's a flipped lecture. All the courses are streamed. Participation is a fifth of the grade. That one's for you to decide. So halfway through the semester, I'll ask you like, what's your current assessment of your own participation? Some examples of like exemplary A-level work could be like, so if you're coming, like I've come to 90% of the classes, I have 3 people in the class, and we always like work together to work on problems, and we have questions, and I'm not the one asking them, but my friend does, and we kind of work on solutions to that. That's a great way of saying, yes, A-level work as participation. If you're like doing remote things, then again, you have to be like, build your own sort of participation, but maybe you have like a text group, or maybe you meet with people at different times, like maybe not during the class time, but you meet up to review or go through readings or something, like you have some kind of connection to other people in the class. Sometimes it's people that have taken the class, like I've seen that as like part of the participation review. Like I met with somebody who had taken this class last year, and they helped me a lot with these things, and I passed that to other people in the class. But somehow, like, what's your learning community? How are you maintaining, how are you growing that, like your little garden of learners around you? Make sense? So, but it's up to you, like how you want to do that. So halfway you'll get progress report, and then at the end of the semester we'll throw that grade away, and you'll submit like a final, this is what I did. Maybe halfway I thought it was a C because I felt really disconnected, but now I've been in class, I have I have people that I work with, I know who to contact, and now I have a learning community, A-level participation. Sound good? I know as engineers, you're like very rigorous. Like, you need 3 discussion posts plus 60% in-class participation, and you need to raise your hand that only works for so many people. And I want you to be able to tell your story. I want to hear what you did, not what I told you to do. But just tell me what to do. All right, and then homeworks and quizzes, we were just talking about those. We'll build the quizzes together, but you'll do them on your own. Homework, we'll kind of do that together in class. Projects, we'll do a lot of like the startup of the project, but some of there's always like questions about like why did this work, or how would you change it, or what did you learn, and that kind of stuff. Usually it's better to like reflect on it and answer those on your own. So there's most of the project is in class, at least getting through the bulk of make the graphs, make the calculations, and then maybe another like 30 minutes of stuff that you have to do outside class to finish it up. Is there a hand? It's quiet. It's a set. Have you had 3 classes? Already 2 classes, or is this the first class of the day? A lot of people showed up very early. It's a second, third, some second. It should be like warmed up, like ready. We're in it now. We're moving. All right, so you know a little bit about how, at least like rough idea of how it's gonna work, and then exact idea on how it'll be graded. Is there any misalignment between the two? Like, project should be 50% or something.
What's like the final independent?
Yeah, this one, I don't know why I dropped it down there, because this was just supposed to be like right up there. I don't know what happened in the last revision. And then a non-lies is, I don't know what that's supposed to mean. Analyze, it's a typo. But that looks like a typo to me. I don't know what happened. So the reason, yeah, that is a great question about like, what is that independent project? We're gonna reserve the last 2 weeks of the semester just to work on like some kind of like reflection or like an individual project. So that's good. And it can really be anything, as long as you're taking like some kind of topics or ideas from what we were covering in the class and applying it somehow. My main goal is that you leave the class with like a story about like why you feel you're an expert, or even that you're proficient in this kind of material. So when someone says down in the interview like, oh, I see you were in dynamics, what was that class like? Rather than just being like, I got an A, and now the conversation's over. You can say like, oh, it was a great class. I took the last 2 weeks of the semester for an independent study. I looked into robotics. I wanted to simplify it to make it manageable, so I did a 2 degree of freedom robotic system. I looked at some of the kinematics of the motion and then kind of plotted out some different paths. And now the interviewer's like, whoa, this person really knows what they're talking about, rather than like, I don't know what this person's talking about. Like, an A is what? Like, who knows what an A is? Well, an A from UConn is good. UConn's a great place. But stories, people love stories. They're great. So that's the end goal of the class. 2 weeks. No final, no midterm. I guess that's the other part of that. There's always a scheduled final, so it will be there, but I won't be there for the scheduled final, so you don't have to be there. You can do whatever you want. It is a free classroom for like 2 hours or something, so you could show up, have a pizza party, donuts. Cool. Other questions? So we know roughly what we're doing. At least I told you what we're doing. You have no idea what you're in for, though. But why are we doing this is the next question. Why are we here? Specifically, why are you here? I know it's required. Like, I know someone told you you can't get this degree without this class. but back up for a second and look at why do you think someone told you this is a required class? So like you're gonna leave this, at least like the main theory of education is like you take classes to like become like understand vocabulary and methods and processes. So like what are the thing what for you, why are you in this class? Like what's gonna change by the end of the class? So take a minute. You can either write it down or write it down and tell someone next to you, or just brainstorm with somebody next to you. But why are you here? All right, I didn't stop in on everyone, but I'll write down a couple of things that came up. And then so a couple of times the idea of like foundational knowledge came up, and I thought that was interesting. So I wanted to ask, like, if you were talking about like this is a foundation for something, what was like, what are you imagining is like your house? What's it built out of? If dynamics is your foundation, what's built on top of it? Yeah. A career? Career in what? Like what kind of career?
The foundation was built by schooling and actual walls, house, or
Oh, like I meant like specifically what career? Like
I'm looking to
patent law? Yep. Remember, as a patent law, like one of the main things, like I think I was talking to a patent lawyer. He said 3/4 of his job is explaining to people that you can't have infinite energy maker, like perpetual motion machines can't exist. It's like every year there's like thousands of patents that come in. Like this one, once you start it, you never have to stop it. It's like that's perpetual motion, guys. Like there's a second law for a reason, and it's a law, not a recommendation. But so like foundational knowledge for even like patent law, like understanding mechanisms. So like, and that was one thing that came up, like mechanisms and moving parts. I guess I wrote that twice, huh? What else? Were there other like foundational, like what's your next step if this is your foundation? Or did this only come up did I just happen to pick the section of class that was talking about foundations? Everybody else is like, foundation? What are you talking about? No? So one way to think about this, and the reason that kind of struck me, is that like dynamics is the foundation of solid mechanics and fluid mechanics. Like, because in both of those they use the same exact laws of physics as dynamics. The only difference is now you also have something called like a material model. It's called like a constitutive model that describes how kinematics and kinetics are connected in another way. So we have Newton's second law that tells us how forces create motion. And then in whether it's solids or fluids, there's another law, like Hooke's law, or what's the fluid shear force is shear rate of shear. Newtonian, yeah, Newtonian fluid. That's the one. Or a Newtonian fluid or something, like some kind of thing that describes like how material deforms. So it could be like for solid mechanics or for fluid mechanics, but it's all now it's just mechanics of materials instead of just like mechanics. So here we're saying like everything's a rigid body. No matter how much force I put on it, it's not going to bend. It's just there. Or if it is bending, it's negligible, because the bigger thing that I care about is the fact that it's spinning around in a circle, or I'm using it as like a baseball bat to impart an impulse onto something. Watermelon, Gallagher. Then there was like understand motion. Did this cover, what else came up? Did this not cover what you're talking about? Or everyone was like, nope, that's me. Nothing else came up? Nothing? Come on, you gotta be like, I know we're engineers, but you're still creative individuals. Not all like totally groupthink yet. I don't think yet. There's something different that came up. So this is it. Build a foundation, understand motion. Those are the two things that we want to do. Yep.
You could have like predicting motion.
Understand, predict. Predict motion. Yeah. So being able to like take something, all right, understand how it works, let me change it. I can make a prediction for, so predictions are good. Predictions are great for engineers. Like if you have a model that accurately predicts something, you can do so much. Like now you can start the real design work. Like let's vary this, we'll optimize that, change this, all sorts of good stuff. Predicting motion. Ooh, bless you. Yeah.
It's like applying what you know to real physical scenarios as opposed to doing problems that are just hypothetical. That's something that actually works.
Applying theory to application. Something, did I cover that okay? Apply theory to applications, yeah. Hopefully we do that. Hopefully we take a lot of our classes and apply the class to some kind of application, but sometimes it gets, I remember, and when I was like studying engineering, sometimes it felt pretty far from reality of like the stuff that I was doing on paper. Like, is this even possible to make this into something useful? Yeah, like at the time learning about Gibbs free energy, like I do not understand this, nor do I have any idea how I'm going to turn a Gibbs free energy model into something. Since then, I've kind of figured out like how useful it is. It's like a means of like material science and those kind of things. But at the time, sometimes it feels like so far away. Even entropy. Entropy is a really tough one. Have you done thermo yet? Entropy feels so nebulous as like a concept. Like the math to do it of like, okay, here's entropy, has to go up, or it can be equal. Cool. Got it. And then trying to turn that into like, all right, let me go measure the entropy of this engine. Like, no, can't do it. But it is a really useful like theory to try to apply, and gives you some nice like upper limits to what you can work on. Okay, cool. So understand. So it sounds like we do want to understand motion, right? Let's come down. So if we're trying to understand motion, there's two parts to it: kinematics and kinetics. There's some stuff written up here, and you're welcome to read it. But let's start off with the idea of kinematics, because that one you've heard kinematics a lot. But I want you to think about what is kinematics. So take a second. You can ask a neighbor or tell a neighbor, shout it from the rooftop. Well, maybe not the rooftop, but like, this is it. This is kinematics. But that's the first step. What is kinematics? So we're trying to identify what is kinematics. What do you think? So these were the things that I had heard about, like kinematics. Again, I didn't like interview everybody, but what else did I miss? Yeah. Oh, vector. Yep. Vector based. It could, like, we can describe motion with scalars, right? Like we can say it's a distance, and that distance is so vector based, scalar based. So when we're choosing, like, is it a vector, is it a scalar? Again, like if you use this as a foundation for mechanics of fluids or materials, now you're talking like tensors, like stress is now a matrix full of things, or strain. Specific strain is more the kinematic measure. Sorry, was there? Oh no. Right. So description of motion, measuring motion. You could say you're measuring a vector of motion or describing vectors. So what is this? Like one thing that came up was like kinematics is motions and forces. But I didn't write forces up here because actually forces, and the goal here is more like just talking it through, not to say like wrong, right, but why is force not a kinematic thing? Yeah. It's kinetic, okay. It's kinetic. Because it doesn't fit in our, if it's one or the other, it's just not this, it's that. So for kinematics, like the general thing that we're kind of describing here is that it's the definitions and like description of, it's the geometry of motion. Like how are we actually, we know something's moving. How do we define that movement? Are we measuring it? Or do we have an equation? Like the kinematic equations, there's no force involved in the kinematic equation, right? It's not saying that F equals x of t of something of something of something. It's just x of t is x0 plus v0t minus g over 2t squared. Like it's all time and positions. So it's the like definitions and description of that geometry of motion. That's like our kinematics, geometry of motion. This was like, it's hard. So a lot of times it's kind of weird to like take a class in something like this because this all happened over the course of like 1,000 or more than 1,000 years of actually how do we describe motion. And like originally there were like two schools of thought of like everything's moving versus nothing can ever move. Like everything, there's motion is impossible. It's like, what? How is that? And now we have like a whole Cartesian system of like, we can describe it as a vector, we can have scalars, like there's all this different stuff. But kinematics is our general, like, whether it's an equation or actual like hard measured values, and we can take derivatives of those or anything. Okay. So if that's describing our motion, why did I write Doesn't help to write the same word twice, huh? What is kinetic? What makes it a kinetic thing? Yep.
So you introduce a force into the geometry of motion.
So we have so we already have motion, and then apply a force.
Or the forces of the motion, rather.
Forces of motion. Forces. So maybe forces. Definitely, our forces are forces of motion. You can, yeah, it doesn't have to be quiet. You can ask somebody. We still got we got like 2 more minutes, right? We'll figure this out. Take 2 minutes, and then we'll write up what we think. Try going to the back. What is kinetics? So one other big topic came up was like changes in energy. Like I had kinetic energy, now I have potential energy. That idea. So what do you think connects those ideas? Did anyone have like an epiphany? Yeah. So conservation of energy might be like our kinetic description of like this is my kinetic thing that I'm describing. So energy, and whether you use force or energy, you end up with the same like equations. They all end up coming back to the same thing. So what do you think, like general, like before we described motion, now what are we doing with kinetics if we're talking forces and energy? I know, class is over. It's like, dude, wrap it up. Come on, man. All right, so kinetic is like the how. How did this happen? Why is it happening? Like, is it a force involved? Is there work input? Is there like an impact? Did something hit something else? Like, why is this motion happening? So this is like the what and the how are the two things. What happened? How did it move? And then how did it move? Like, what were the forces or energies involved? That's kind of the two things there, kinematic, kinetic. All right, thanks a lot. Be back on Friday. Thanks.
Thank you.
Thanks a lot.